morning, everybody. I'd like to present here our experience at NUMECA in the area of computational fluid dynamics, and the activities I labeled at exascale horizon, because that's where LUMI is going. It's getting close to the exascale level. And the main focus I want to put is also the necessity for industry to have access to high performance computing applications. And I will demonstrate that with the main issue in computational fluid dynamics and in fluid dynamic simulations in general, which are related to turbulence, to prediction of turbulence. So just two words on NUMECA. We are a spin-off of the Vrije Universiteit Brussels, and with around 150 employees today. We have many hundreds of customers in many areas, in automotive, in aerospace, in aeronautics, in marine, and so on. So I'd like to introduce first what is the issue about turbulence modeling, which is the blocking item today in all flow simulations at an industrial level. And so along these lines, we have a large experience in high performance computing through through our own developments and through several projects, which I will describe shortly. So let me move on. Let me here show one example of the current status of turbulence modeling. So that is here a generic aircraft model, which is called the CRM for Common Research Model. It has been used very widely since many years to assess the accuracy of turbulence modeling in computational fluid dynamic solvers. And if we look at this plot here, the issue on the right, this is prediction of drag, which is the main quantity for an aircraft. The drag will determine the fuel consumption over a flight. So it has fundamental applications on the whole economy of commercial aircraft. And so what you see here on the right is the output of a workshop which was held a few years ago to assess how accurate do various codes, research codes, commercial codes, predict the drag. And you can see here that there is a wide variation of prediction. Each of these curves is a different code. And in abscissa, you have the number of points. So at the lower end, you have a simulation with 100 million points, and some converge. If you look at the values, not all the codes do converge to the right value, to the experimental value. And to indicate the level of accuracy that industry requires, one graduation, as you can see here, is 5 counts. So 1 count on drag is 1 unit on the 4th decimal place. So that indicates what is the accuracy required by industry. They require an accuracy of the order of 1 count. And so we are far away from it today, as can be seen here. And if we look at other curve, which is the moment in function of incidence, what here again, this is the output of a workshop, giving the discrepancy between various codes. And we have to look at what happens here when the angle of attack increases. So then there is flow separation. And the key issue today is that there are hundreds of turbulence models that people have published and developed over the last 50 years, but none of them is reliable when it comes to separated flows. And separated flows are present everywhere. So here, if we look at the shear stress lines on the wing, you can see by having different turbulence models, the significant difference in prediction between different models. And here, this model predicts separation here at the intersection between the wing and the fuselage. Here, there is no separation, and so on. So that is the main issue. So what is the way to go around these limitations, particularly with a separated flow? And I don't mention here the issue of laminar turbulent transition, which is also very fundamental and very difficult to model in the approach. The approach that I showed is called Reynolds average Navier-Stokes, RANS. So it means that we average over all the turbulent fluctuations at all scales, and that introduces some quantities that are called Reynolds stresses. And the turbulence models are semi-empirical models that provide laws or the transport equations for some quantities related to the Reynolds stresses. So without going into the details, how can we overcome the current limitation? So the only way to overcome the current limitation is to move away from RANS, from Reynolds average, to resolving the turbulent fluctuations. So we have the ultimate is what is called direct numerical simulations, where all the turbulent fluctuations at all scales are modeled by solving the fundamental Navier-Stokes equations. And then there are various sub-levels depending on the available resources, like large eddy simulation, where one models the large scales of turbulence, but the smallest scales where one calculates the larger scales, but we model the smaller scales. So this is summarized in the chart going from Reynolds average Navier-Stokes to DNS. And the LES, different variants of DNS LES, of course, are much, much more expensive, and they can be considered only with thanks to the developing high-performance computing hardware. And as of today, I don't have time here to go to the details, but if we want to do a DNS simulation of a full aircraft, that requires facilities and computing power much, much above the exascale. So whatever the power of a high-performance computing system, it will up to now never be enough to fulfill the ultimate objective of doing DNS on a complete aircraft. But let me show here this example of a car aerodynamics. So here on the left, you have the simulation from Reynolds averaged simulation, where you can see the streamlines and the wake here, the vortices in the wake. And on the right, you see the LES type simulation. So these are two aspects of actually the same reality. It depends how you scale, at what level you want to look at the flow. So on the right, you have the flow in its closer reality. And if you average all the fluctuations over time, you obtain the vision on the left. So these are two aspects of the same reality. One is instantaneous and the other is average. But we need the instantaneous simulation today to obtain more accurate representation of the average flow. And just to put it in a practical, from a practical standpoint, if we look at an aircraft, the drag of an aircraft and the fuel consumption over flight are averaged quantities. We are not interested in the instantaneous value of the friction, but over the average quantity over a flight at a given regime. So at NUMECA, we have been, of course, developing both software codes for LES, DNS simulation, which require high accuracy. So we need a new generation of CFD solvers to allow the accuracy that is needed for these high fidelity simulations. And that is a driver for industry to exploit more and more high performance computing. If we do a high fidelity simulation of the type I show here, for instance, the industry will accept such a simulation if we guarantee a return time of less than 1 day, whatever the number of processors. Actually, they don't care if one has to use 1,000 or 10,000 of processors. Some of the industries we work with, for instance, in the automotive area, have installed for their facilities with more than 100,000 cores. So that's not the issue. The issue is return time. And that is guiding our developments and also the developments of our partners and in that objective. And this is supported by several European projects in particular. And one of them is a project that we are coordinating, which is ongoing, which is called Hi-Fi Turb. Yeah, this is an example here of a transitional high fidelity simulation. The objective of Hi-Fi Turb is to develop new generation of turbulence models for separated flows. But the methodology we have put forward is the following, that in order to obtain new models with new physics, we have defined a series of test cases, which all relatively simple, but all have different variants of separated flows, and for which we run high fidelity DNS or world resolved LES simulation. And that can only be done on the current petascale machines with high order methods. So each case, here you have some examples of 5 reference test cases with different, this is a shock-induced separation. On the left here, this is a pressure gradient separation. In that test case is a separation typical of a wing-body combination. The last one is a diffuser with divergent walls, which natural separation as internal flows. And so for each of these cases, we run that with up to 1 billion data points, and each test case generates, we extract from each case 175 turbulent averaged quantity, which are representative of Reynolds stresses and turbulent properties, and they have to be analyzed. So if we have a run with 1 billion point, that represents 175 billion data. So we introduce a work package that exploits various artificial intelligence and machine learning techniques to investigate correlations and to detect and to derive unknown correlations between these quantities And this is guided by turbulent expert groups where, for those of you who would be familiar with turbulence modeling, you will recognize the names here of Mentes, Pallard, Leschiner, and so on. They are all part of the project. And so just within that project, we have had access and have access to some of the most advanced European Tier 0 centers. We have been running data on the Barcelona supercomputer, Mare Nostrum. We have currently access to Marconi 100 at Cineca in Italy. We have an ongoing project on Irene at CEA in France. And as I said, we are exploiting the maximum capacity, running, as I said, billions of points. Just one example here of one of the test cases, which is the turbine cascade with end walls. If you have never seen the details of turbulence, you can see it here. This is at different orders of accuracy. This is the diffuser that has been run on Mare Nostrum, and here we have we compare in black the black lines our results with the reference results for DNS. One can hardly see the difference, so that was quite satisfying that we could check the whole simulation process. And that test case is ongoing now on Irene for larger Reynolds numbers. And so the last point I want to describe is the InSight project. That is a current project we have on Summit in the United States. Well, for those who are not familiar, InSight is the US equivalent of PRAISE. It is one of the very, very few programs in the United States where non-US citizens can apply for. And so we have a project ongoing for understanding the instability mechanisms in axial compressors based on a well-known configuration, which is a transonic rotor 37. And so it's a quite challenging project because instability in compressors implies many passages and very complex physics. So that is a 2 years project. We are now in the second year. We have 500,000 node hours for this year. And well, each node has 2 IBM 22 core CPUs and 6 NVIDIA V100 GPUs. And we have been exploiting and are still exploiting significantly the use of GPUs. And I was very pleased listening to Dr. Manninen that LUMI will be heavily focused on GPU because it is very, very important. Just here to show you some of the simulation. This is, here you have a shock wave intersecting with the boundary layer, and there are different instabilities that have hardly been studied up to now that are detected. So it's this high performance computing, high fidelity simulations are highly instructive to detect physics that you'll never see otherwise. And in terms of GPU, we have a very, very excellent scalability on the CPU, and moving to the GPU at different levels of our implementation. In the first loop, we finally obtained a speed up of 9.5 between the CPU, but with further developments, we have the scalability. In blue here, we have the CPU scalability that is in function of the number of CPU and GPU. So that these tests were done by having one GPU paired with one CPU. And we use OpenACC for these NVIDIA GPUs. The objective is to go up to above 500 million degrees of freedom. And what we can see here is that depending on the number of cores, for low numbers of cores, where we have large number of points for each partition, we can achieve a speed up of around 80. But when we increase the number of partitions of cores and GPUs, the CPU scalability is very excellent, remains practically constant. But we still have some work to do to improve the GPU scalability when reducing the number of points per partition, and that might be difficult, because once we have too little point, the communication becomes a bottleneck. But that is an ongoing process. But anyhow, achieving 80x speed up, we were very pleased to see that. So in conclusion, I'd like to emphasize that HPC is a major basic item for CFD applications in industry. And we know, of course, the importance for research, but industry is becoming more and more aware of the needs. And in the cases I mentioned here of turbulence simulation, the key bottleneck, as I mentioned earlier, is the return time. So, and I can assure you that we have enough information that industry will adopt high fidelity simulations if this return time is satisfied. And today, with the access of the cloud, it makes the access by industry of high performance computing also more practically. And the role of GPU is absolutely essential to match the objective of a return time of less than 1 day for, say, 500 million data points or more. Without GPU, it is just inconceivable. And so we expect that the LUMI facility will be a major factor in support of the European high-tech industry, and in a world that is, as we all know, very highly competitive.